In this video, I'll be discussing a number theory problem. Find all 3-digit numbers such that the last 3 digits of the square of this number is the original 3-digit number. In this example, the such 3-digit number is 625, and then the perfect square of 625 is 39,625, and then the last 3 digits of 39,625 is 625, which satisfy the conditions of the 3-digit number. So now, I'm going to find all of the possible 3-digit numbers. So we already know one of the numbers will be 625. So you can let this 3-digit number be m. So what should we do with m? Well, hopefully we can get some relationship between m and a perfect square. And maybe if we can factorize something related to m, like for example, in this one, we know that 625 perfect square will equal to 39,625. Well, the perfect square, we can find a relationship here. This will equal to 39,000 plus 625, which will be 1,000 times 39 plus 625. You may see where I'm going at right now. So this will lead us to our discovery here. M squared can be written as, using the property, 1,000 times some certain number. An example here is 39. So it's 1,000k, let the number be k plus m. And then now, we are actually all set to solve this problem. Because earlier I said that we want to find some factorization and relationship between m squared and m. And there we have it. M squared minus m equals to 1,000k. When I say factor, it means that if I can factor 1,000k, and we can factor m squared minus m, which is m times m minus 1. 1,000k will equal to k times 2 cubed times 5 cubed. So factor means that m may contain one of these factors and m minus 1 will contain the other factor. Why can't they contain both of these factors at the same time or share a factor? Well, this is because note that consecutive integers are co-prime. This is the identity. Co-prime. Co-prime meaning that these two are relatively prime integers, so they share no common factors except 1. So this means that m and m minus 1, only one of them can have a factor of 5 cubed, and the other one can have a factor of 2 cubed. They can't both share a factor of 2 or 5, because that is the co-prime rule. So now we can split into cases. The first case and the second case are going to be similar. The first case is where m has a factor of 5 cubed, and the second case will be m minus 1 has a factor of 5 cubed. So m has factor of 5 cubed. This means that m has factor of 5 cubed. M can equal to 125. Now, will the next one be 250? Well, no, because note that if m equals to 250, then that means that we are, for a correct answer though, we are looking for m minus 1. The corresponding m minus 1 has a factor of 2 cubed, which is 8. This means that m cannot have a factor of 2. Then they won't be co-prime because they share a factor of 2. So you skip the even ones and you get 375. Skips 500, go to 625. Showing an example, is a working one. Then skips 750, go to 875. That's it. The corresponding m minus 1 will be 124, 374, 624, and 874. For the correct m, you want the following m minus 1 to have a factor of 2 cubed. And you see, the only working one will be 624. That means that m can equal to 625. Now the second case is the opposite. m minus 1 has factor of 5 cubed. m minus 1 will equal to 125, 375, 625, and 875. m will equal to 126, 376, 626, 876. And now, note that m will have m equals to 376, m minus 1, 375. m has the factor of 2 cubed. And it's the only working one that has a factor of 2 cubed. So this means that m equals to 625 or m equals to 376. That is how you solve this problem. The key point is noticing the relationship between m squared and m, and then factorizing m squared and factorizing k and 1000, and knowing that consecutive numbers are coprime. Then we can let two cases where m minus 1 has a factor of 5 cubed in it. And then if the next factor, m minus 1 or m, has a factor of 2 to the power 3, which is 8, then the case is correct. And then this led us to find the answer to the problem for 625 or 376. That is how you solve this problem. Thank you for watching.